With millions of AI models popping up all the time, it really feels like we're standing at the edge of this vast, new, unexplored universe. Every single day, thousands of new stars and galaxies of code are just lighting up. But how do we even begin to make sense of this massive, expanding cosmos? Well, the answer might actually come from looking back at how we started to understand our own world.
This is such a powerful idea. Think about it like this. For centuries, biologists studied individual animals. One plant here, one creature there, all in isolation. But the real aha moments, the huge breakthroughs like Darwin's theory of evolution, they only happened when scientists zoomed out and started looking at entire populations and how they all connect. And right now, AI, well, it's kind of stuck in that individual specimen phase.
And that really is the heart of what we're talking about today. What if we could just zoom out from looking at one single AI model at a time, and instead see the entire ecosystem all at once? What kind of patterns, what kind of evolution, what incredible insights would we find if we could do that?
To answer that, researchers are proposing a pretty radical new tool. It's about moving away from just having, a giant, boring list of models and starting to see them for what they really are, this deeply interconnected living ecosystem. They're calling it the Model Atlas. And this isn't just some catalog. It's a dynamic graph. It's a map that shows every single model, what it can do, and this is the important part, how it's related to all the others through processes like fine-tuning, which is kind of like specializing a model for a new job, or quantization, which is about making it smaller and way more efficient.
The easiest way to wrap your head around it is with this map metaphor. It's perfect. Each AI model is like a city on this giant map, and all the transformations that turn one model into another, like fine-tuning it on new data, those are the roads and highways connecting all the cities, showing you exactly how information and evolution flow through the system.
And once you start looking at the atlas, you see these fascinating patterns just pop out. For example, the Llama region of the map, it's like this sprawling, chaotic megacity, incredibly complex, super deep, with a huge diversity of roads. People are using every technique in the book to modify these models. But then you look over at the Stable Diffusion region, and it's more like a neat, organized suburb. Much simpler, more uniform, primarily using fine-tuning. This lets us literally see how different AI communities build and innovate. It's amazing.
Okay, so this is all cool. But why? Why go to all this trouble to map this universe? What's the real benefit here? Well, it turns out having this map unlocks some absolutely incredible capabilities.
The applications really fall into three main buckets. First, the Atlas lets us perform what's called model forensics to trace a model's whole history. Second, we can do meta-ML research to see the big picture trends. And third, and maybe most practically, it powers model discovery, helping developers find the exact tool they need without having to reinvent the wheel.
So let's dig into that first one, model forensics. And honestly, it's pretty much AI archaeology. With the Atlas, you can pick any model and dig into its entire lineage, what data it was trained on, who its ancestors were, every little change made along the way. This is a total game changer for stuff like tracking intellectual property or making sure scientific results can actually be reproduced. Then you've got meta-ML research. And if forensics was archaeology, think of this as AI sociology. Now, looking at the whole map, we can see how different communities work. Like, are the computer vision researchers adopting new techniques as fast as the language model folks are? The Atlas makes these trends totally visible, showing us where knowledge is flowing, and maybe more importantly, where it isn't. And check this out, this is a perfect example of what I'm talking about. The Atlas shows that model merging, this technique for combining two different models, is 35 times more common in natural language processing than in computer vision. 35 times! That doesn't just tell us what's happening. It screams that there's a huge opportunity here for vision researchers to explore a really powerful technique that they've been mostly ignoring.
And finally, there's model discovery, which might be the most practical application of all. It's basically a GPS for the AI universe. Instead of training a brand new model from scratch, which is incredibly expensive and burns a ton of energy, a developer can just use the Atlas to search for an existing model that already does 90% of what they need. It just makes AI development so much more efficient and sustainable.
But here's the catch. There's always a catch, right? We have this incredible concept for a map, but right now we're trying to navigate it with these massive, gaping blank spaces. There's a huge problem of what researchers are calling lost models. And this is the statistic that just blows my mind. Over 60% of publicly available AI models have little to absolutely no documentation.
No info about where they came from, their training data, how they were made, nothing. For all practical purposes, they are completely lost at sea. And the consequences of this are actually really serious. We're talking enormous amounts of resources just wasted, retraining models that already exist somewhere but we just can't find them. All this valuable knowledge from past experiments just vanishes into thin air. And even worse, these breaks in the family tree create huge safety and IP risks, because if a model does something problematic, we have no way to trace it back to its source.
So how do we fix this? How do you fill in these giant blank spaces on the map? Well, this challenge has given rise to a whole fascinating new field you could call AI cartography, the science of charting these unknown digital territories.
The technical term for it is weight space learning, but the core idea is pretty simple. It's about developing methods that can look directly at a model's raw guts, its weights and parameters, and figure out its history and its relationships all on its own, even with zero documentation. It's like learning to read a model's DNA. So how on earth do they do that? Well, they act like detectives, looking for clues. And they found some that are incredibly reliable. For instance, more than 99.7% of the time, a parent model gets uploaded before its child model. Makes sense, right? They also found that quantized or compressed models are almost always an endpoint, a leaf on the family tree with no kids. These sound like simple rules, but they're surprisingly powerful for piecing things together. And this is one of my favorite examples of their detective work. They can now tell the difference between development patterns just by looking at the models. A snake pattern, which you get from saving checkpoints one after another during a long training session, shows a strong link between time and how different the models are. But a fan pattern, where a developer tries out a bunch of different settings from one starting point, shows a really low correlation. Being able to spot the difference is absolutely crucial for drawing the map correctly.
So here's the million-dollar question. Does all this clever detective work actually work? The answer is a resounding yes. I mean, look at these numbers. For the super complex llama family, the old methods could only reconstruct the family tree with about 19% accuracy. These new charting methods, over 80%. For stable diffusion, they jump from 50% all the way to 85%. This is a massive, massive leap forward in our ability to actually map this AI universe.
So what this all means is that we are really at the very beginning of a new age of exploration. The AI universe is expanding faster than we can possibly chart it, but this research gives us the first real maps and the tools to create even better ones. And so the question it leaves us with is this: who are going to be the cartographers of this new world, and what incredible discoveries are still waiting for us out there in the uncharted territories?